Let us now learn about molecular shapes, which is also known as molecular geometries. The very first thing anybody would want to know is this: why should I bother about molecular shapes? What concerns me about the shapes of molecules? And the answer to that is that the way a molecule will behave, its properties, and its functions is highly dependent on its molecular geometry. Now, to determine the molecular geometry of a molecule, we use a very simple theory that is called valence shell electron pair repulsion theory. This has an acronym that is VSEPR theory. VSEPR theory. Some people simply call it Vesper. This theory allows us to predict what a molecule would look like. And if you study chemistry at a higher level, you will see a lot more about how shapes of molecules determine their properties and functions. The first thing is this: what is the Vesper theory? Think of it this way. Each atom has valence electrons, and electrons are negatively charged, which means that two atoms do not want to be too close to each other because the valence electrons in both atoms will repel like charges will repel. And that is the meaning of the Vesper theory. The electron pairs in the valence shell of an atom will repel. Now, with that understanding, let us now look at the molecular shapes of different types of molecules. Let us take a look at a situation where we have only two atoms in a molecule. Let me denote that as A2. A2 is a generic formula for any diatomic molecule. How best can these two atoms bond to each other? The only way two atoms can bond to each other is simply by directly connecting to each other. There is no other way. And because that is the only way, the molecular geometry for diatomic molecules will be linear, because this is like a straight line. It is linear. Let us take a look at a model of diatomic molecules. The purple atom here, let us connect one other atom to it. Now, that is a diatomic molecule, only two atoms. As you can see, it is simply a molecular geometry that is linear. If you look at the bottom of your screen, you will see linear as the molecular geometry. An example of A2 type molecules will be hydrogen gas, which means that after drawing the Lewis structure for hydrogen gas, this is the best shape you can get for a diatomic molecule. Let us now take a look at if we have 3 atoms in a molecule. If a molecule has 3 atoms, one of them has to be the central atom. Let me represent the central atom as A. So A is the central atom. And the remaining 2 atoms, let me represent them as B. So we will call this the generic formula for any molecule that has 3 atoms. Now, I want to make a very important distinction here. The central atom in this molecule has no lone pair on it. No lone pair on the central atom. Why do I need to make that distinction? I will explain momentarily. Now let us continue with AB2. If there is no lone pair on the central atom, how best can we arrange the 2 outer atoms around the central atom? And if you are thinking the way I am thinking, if my central atom is like this, the 2 outer atoms will literally be at arm's length to each other if they want to stay as far away as they possibly can from each other using the VSEPR theory. Remember, the electrons in the valence shell want to be as far away from one another as they possibly can. Let us take a look at the model of a molecule that has no lone pair on the central atom and has 2 outer atoms. Now, the central atom is the purple atom. Let us connect one atom to it and then connect another atom to it. This is the best possible shape we can get for any molecule that has 3 atoms and the central atom has no lone pair on it. And if you look at the molecular geometry at the bottom, it also says linear. So the molecular geometry for AB2 type molecule is linear. Let us take a look at an example of this. What is the molecular geometry for carbon dioxide? If you draw the Lewis structure for CO2, you will get something that looks like this. Anytime you want to determine the geometry of a molecule, you will always begin from the Lewis structure. Let us now build the model for CO2 and take a look at it. As you can see in this model, the molecular geometry is linear, and the 2 oxygen atoms that are denoted as the orange balls, they are literally 180 degrees away from each other. So the molecular geometry for AB2 type molecule is linear. But again, let me stress the fact that we do not have any lone pair on the central atom. If we do, the molecular geometry will be different. We will consider that in a moment. Also, another thing to note here is that angle BAB is 180 degrees. Let us now take a look at molecules that have 4 atoms in them. If a molecule has 4 atoms in it, we can simply denote such a molecule as AB3. What does that mean? It means that we are assuming that the A is going to be the central atom and the 3B atoms will be the outer atoms. But again, this comes with a very important caveat. There would be no lone pair on the central atom. It is an extremely important thing to note. How best can the 3 outer atoms arrange themselves around the central atom? If you're thinking what I'm thinking, you would be thinking that they would arrange themselves around the central atom like a triangle. Let us take a look at the model of AB3 type molecules. The purple ball is still the central atom. Now let us attach 3 outer atoms to it. Now take a look at it. You will see that the 3 outer atoms arranged themselves around the central atom like a triangle. Now, one other thing to note here is that all the atoms are in the same plane. What does that mean? That means this molecule is flat. The 3 outer atoms and the central atom are in the same plane. Now, note that the angle BAB is 120 degrees and the molecular geometry is called Trigonal Planar. Why is it called Trigonal Planar? Because it looks like a triangle. That is the trigonal part. And all the atoms are in the same plane. So the molecular geometry is trigonal planar. And the angle BAB, each of the angles is 120 degrees. Again, let me stress the fact that there is no lone pair on the central atom for the AB3 type molecule we are considering right now. Let us take a look at an example. An example will be BF3. If you draw the Lewis structure for BF3, you should get something that looks like this. Remember, boron is an exception to the octet rule. This molecule, if you build a model for it, the molecular geometry will be trigonal planar. Let us take a look at the model for BF3. The model for BF3 looks like this. As you can see, the three outer fluorine atoms, they are positioned like a triangle around the central atom. And the angle FBF is 120 degrees. And if you look at the molecular geometry at the bottom, you will see that it is trigonal planar. Let us now take a look at when you have 5 atoms in a molecule, which we will call AB4 type molecule. In AB4 type molecule, again, remember, A is representing our central atom, and there is no lone pair on the central atom. So this is the question. How best can the 4 B atoms position themselves around the central A atom? Anytime I ask my students in the classroom, this is what most of them tell me. That is actually not true. Let us take a look at the model for AB4 type. So this is wrong. The purple atom is the central atom. Let us now add 4 outer atoms to it. 1, 2, 3, 4. If you look at the AB4 type molecule, you will see what I mean. It is not constructed like a plus sign. No. It looks as if 3 of them are like the legs of a tripod, and the 4th one is like a camera on top of the tripod. Another thing to note about this model is that each angle BAB is 109.5 degrees. The name of this shape, the molecular geometry, is tetrahedral, as you can see at the bottom of your screen. So let us now look at an example. An example of AB4 type molecule is CH4, which is also called methane. If you draw the Lewis structure for CH4, you should get something that looks like this. And the molecular geometry is tetrahedral. Let us now take a look at situations where we have lone pairs on the central atom. Let us take a look at a generic formula AB2E. What does that mean? A will represent our central atom, and E will represent the lone pair on the central atom, while B will represent the outer atoms. How will the 2 outer atoms and the lone pair arrange themselves around the central atom? Let us take a look at the model to see for ourselves. The purple ball will still represent the central atom. Now, we have two outer atoms, and we have a lone pair on the central atom. This is what the shape of the molecule would look like. As you can see, the lone pair is occupying a position that an atom would normally occupy. So it looks like a AB3 type model. So if you look at the electron geometry, if you remember, AB3 type models would have trigonal planar geometry. So if we consider the lone pair as an atom, that is when we look at the electron geometry. You will see that I did not mention anything about electron geometry before, because then we did not have any lone pair on the central atom. But what is the molecular geometry? The molecular geometry is the actual geometry of the molecule, because electrons are not actually atoms. So what is the molecular geometry? It is bent. Let us draw that to see for ourselves. So A is our central atom. These are the two outer atoms, and this is the lone pair. As you can see, it looks like a bent molecule. Now, the actual angle here is usually dependent on the types of atoms that B's are. But one thing is that this angle will be less than 120 degrees. Why will it be less than 120 degrees? Because in AB3 type molecule, if you consider the lone pair as an atom, the ideal angle would be 120 degrees. However, a lone pair will occupy more space than an atom, because the lone pair is not constrained, and electrons are not only particles, they are waves, so they can spread around. As a result, this angle will be less than 120 degrees. Let us take a look at an example of a molecule like this. Sulfur dioxide. I want you to try to draw the Lewis structure before you look at my answer. Now, if you draw the Lewis structure for SO2, you should get something that looks like this. Let us take a look at the model for SO2. As you can see from the model, if you consider the lone pair on the central atom as an atom, the electron geometry will be trigonal planar, because it then would look like AB3 type. However, the actual geometry, the molecular geometry, as you can see at the bottom of your screen, is bent. So for SO2, we will have two types of geometries: the molecular geometry is bent. The electron geometry, which means we are considering the lone pair as an atom, is trigonal planar. Now, let me again repeat something here. the lone pair we are considering is only on the central atom. We do not really care about the lone pair on the outer atoms. Let us take a look at another generic formula with lone pairs on it. Let us take a look at AB2, E2. By this, again, let me remind you, A is the central atom. The E's here are the lone pairs on the central atom. The B's are the outer atoms. How will the shape of this molecule appear to us? Let us take a look at a model and then we will draw it. Let us now add two atoms to the central purple atom. And let us add two lone pairs. As you can see, the two lone pairs are not on opposite sides of each other. They are side by side, and if the lone pairs had been atoms, all the outer atoms will have an ideal angle of 109.5. But the lone pairs are actually not atoms. So let us take a look at the geometries. The electron geometry, which is assuming that the lone pairs are like atoms, will be tetrahedral, because then this will be like a B4 type molecule. However, since they are not really atoms, the molecular geometry is actually bent, as you can see at the bottom of your screen. So let us draw the structure. Our central atom A has two lone pairs on it and two outer atoms. What is an example of a molecule like this? An example is water. If you draw the Lewis structure for H2O, you should end up with something that looks like this, which means that the molecular geometry for water is bent, and the electron geometry, if you treat the lone pairs like atoms, will be tetrahedral. The ideal angle here will be less than 109.5, although in the model it looks like 109.5, but it will be less than 109.5 because the lone pairs will actually occupy more space. Let us now take a look at another type of molecule that will have lone pairs on the central atom. Let us take a look at AB3 E-type molecule. Again, A is representing the central atom, while E is representing the lone pair on the central atom, while the B's are the outer atoms. Before we draw what the molecule would look like, let us take a look at the model of AB3 E-type molecule. Let us add 3 outer atoms and let us add 1 lone pair. Now, this is what AB3 E-type molecule will look like. 3 outer atoms and 1 lone pair on the central atom. If you look at it properly, you will see that the 3 outer atoms, they are like the legs of a tripod. And if you imagine the lone pair as an atom, then the electron geometry of this shape will be tetrahedral. However, electrons are actually not atoms. So what will be the molecular geometry? On this model, the molecular geometry is labeled as trigonal pyramidal. Why is it so? Let us draw the structure of the molecule to understand why that is the case. A is the central atom. It has a lone pair on it. And we have 3 outer atoms. And the 3 outer atoms, they are like the 3 legs of a tripod. If you connect the 3 legs of the tripod and you look at the overall shape, you will see that it looks like a pyramid. But the 3 legs, they form a triangle at the bottom. That is why the molecular geometry will be trigonal, because the bottom is like a triangle, pyramidal, because the overall shape looks like a pyramid. What type of molecule would look like this? An example will be ammonia, NH3. If you draw the Lewis structure for ammonia, you should get something that looks like this. Now, we have 1 lone pair on the central atom and 3 outer atoms. That is AB3E type molecule. The molecular geometry will be trigonal pyramidal. But as you know, whenever we have a lone pair on the central atom, we also want to look at the electron geometry. The electron geometry will be tetrahedral. Why? Because the lone pair will then be treated as if it is an atom.